Welcome to homework.
In this exercise, we're given a potential function, u of x, that is equal to a positive constant a times the absolute value of x. And we're also given the WKB approximation for the allowed energies. That's the integral between the two turning points A and B of the square root of 2 times the mass times the total energy minus the potential. And this is equal to NH divided by 2. In question A, we have to find what are the classical turning points for this potential given an energy E. Now, the classical turning points are such that the potential energy U of x is equal to the total energy E. Now, U of x is A times the absolute value of x, and this is equal to E. So the absolute value of x is equal to E divided by A, meaning that x is equal to plus or minus E divided by A. These are the classical turning points. In question B, we have to use the integral up here in order to find the allowed energies for the WKB approximation. So we have to integrate from the first classical turning point, which is minus E over A, to the second classical turning point, which is E over A, the following function: 2m times E minus A times the absolute value of x times dx. And this must be equal to nh divided by 2. So let's just do the integral first. Notice that this integral can be separated into two parts. We have the integral from minus e over a to 0 of the square root of 2m times e plus ax. Notice that in the range when x is negative, the absolute value of function is equal to minus x plus 0, the integral from 0 to e over a of 2 times m times z to the minus ax dx. Okay, so basically what I'm going to do is to take this first integral and do a little change of variable. So I'm going to take x prime and call it minus x, such that dx is equal to minus dx prime. So the first integral becomes the integral from e over a to 0, okay, of the square root of 2m e minus ax prime times minus dx prime plus the integral from 0 to e over a, from e over a to e over a of the square root of 2m e minus ax times dx. So basically in the first integral, I'm going to change the order of integration and add a minus sign. So notice that these two integrals are exactly the same, since it doesn't matter if I'm integrating over x prime or x. So this is equal to 2 times the integral from 0 to e over a of the square root of 2m e minus ax dx. Okay. So basically, I'm gonna do again a change in variables. I'm gonna take y and call it e minus ax. Notice that in this case, dy is equal to minus a dx, meaning that dx is equal to minus 1 over a dy. Okay, so the integral becomes 2 times the integral from, notice that when x is equal to 0, y is equal to e, and when x is equal to e over a, y is equal to 0, times the square root of 2m times y times minus dy. So basically I'm going to change the integration order and also add a minus sign. So this is 2 times the square root of 2m times the integral from 0 to e of the square root of 2m. So that's, I'm sorry, the square root of y. So this is 2/3 times y to the 3/2 from 0 to e. So this is 2 times the square root of 2m times 2 over 3. So let me write it as 4 over 3 times e to the 3/2. Okay, and also there should be an over a here. I forgot to add that. I'm sorry. Okay, now everything's correct, and this is equal to nh divided by 2. So now we have to isolate e. Okay, so I'm gonna write this as 2m e cubed to the 1/2 is equal to 3a and h divided by 8. So we get that e cubed is equal to 1 over 2m times 3a and h over 8 squared. So e is equal to 1 over 2m to the 1/3 times 3a and h divided by 8 to the 2/3. I'll notice that 1 over 2m to the 1/3 is equal to 2m to the 2/3 divided by 2m. So I'm going to write it like this. So e is equal to 1 over 2m times 3a n m, actually 3a h m divided by 4 to the 2/3 times n to the 2/3. Okay, so this is the energies, the allowed energies as the exercise asked. And in question C, the exercise wants us to find out whether the difference in energy between two consecutive energy levels, so the energy of n plus 1 minus the energy of n, increases, decreases, or stays the same as n increases. So basically, let me write explicitly, delta E is equal to 3a times m h divided by 4 to 2/3 over 2m times n plus 1 to the 2/3 minus n to the 2/3. In order to find out whether or not this value here increases, decreases, or stays the same as n increases, I'm going to differentiate this with respect to n. Okay, so this is equal to this whole constant here, which I'm not going to bother about. I'm just going to call it b. This is a positive constant times 2/3. So let me write it as 2/3 of b times 1 over n plus 1 to the 1/3 minus 1 over n to the 1/3. Now notice that 1 over n plus 1 to the 1/3 is smaller than 1 over n to the 1/3, meaning that d delta e dn is smaller than 0. Now, if this quantity is smaller than 0, if the derivative of the difference energy with respect to n is smaller than 0, this means that the energy decreases with n. The exercise asks us to compare this with the particle in a box case. Remember that for a particle in a box, the energy is equal to n squared times h squared divided by 2m, 8m L squared. So this means that the energy difference is equal to 2n plus 1 times h squared divided by 8ml squared. So notice that as n increases, the energy difference also increases. So it's different from our case. And also we have to compare it to the case of the harmonic oscillator. In that case, the energy E is equal to h bar omega times n plus 1/2. So delta E is equal to h bar omega, which is constant. Okay, so it remains the same as n increases, which again is different from our case. And this concludes our exercise.